All right, we are on. So we're on. So we just had tests over various things, including logarithms. So yeah, we're going to do everything about logarithms today. And specifically connected with science.
Science.
Yes. So let's create a graph of the logarithm. If I say y is equal to logarithm base 3x, then we ask the question, what does that look like? So we're going to start with setting up a table. We're going to do y is equal to 3 to the x power, and then create the graph based on that. Because this will tell us what points we want to have on the other graph, and so we'll figure out what points we want on this graph. Okay, so we're going to go -2, -1, -1/2, 0, 1/2, 1, and 2. So getting our minds back into mathematics here after a weekend of other things, perhaps. What are the values of y that we get by choosing these particular x values?
-2, 9.
Sorry, it's not 9 because it's a negative exponent.
Oh, 1/9?
1/9.
Sorry.
Okay. -1.
1/3.
1/3. -1/2. What's 3 to the -1/2 power?
1/1.5.
No. It is 1/. It's 1/3 to the 1/2. What's 3 to the 1/2?
Oh, 1/9.
No.
1/9.
1/2 power.
Oh, square root of 3.
1/square root of 3.
Yeah.
Right. What if we put in 0?
1.
And then 1/2?
Square root of 3.
And then 3 is 9.
Yeah.
Okay. So we want decimal numbers then. This is approximately 0.1, approximately 0.3. What would be 1/square root of 3? Approximately? Yes, we need your calculator.
1.7, 1.73.
No, 1/.
Oh, 1/.
What? This is nuts, man. 0.57. How many
So about
numbers do you want?
0.6. This is 1, this is 1.7, this is 3.9. Okay. So what happens when we do the logarithm? What mathematical thing do we do in order to know what these values are for the logarithm? I want to make a similar table of values using logarithms. How do I use my previous table in order to get this table?
You want the inverse one?
I do.
So just flip them over.
I'm just flipping them over. Yes, I am. Just looking at you. You sound like
Oh my, that's what
everyone's
she said.
supposed to know that, but
That's what,
no. Okay, so
yes.
0.1,
That's
negative
what she said.
2, 0.3, negative 1, 0.6, negative 0.5, 1, 0, 1/2, or sorry, 1.7, 0.5, 3, 1, 2. Okay, so what does the logarithm look like?
Logarithm.
It sure does. If I go down here to negative 2, then that's 0.1. So if I go to 0.3, that's negative 1. If I go to 0.6, that's negative 5. 1 is 0. 1.7 is 0.5. 1, 2, 3 is 1, and then out there, way out there, 9 would be 2. So that's what a logarithm is. So then if we ask the question, what is the behavior of this function? What would you tell me? What happens as this thing goes to the right?
It gets bigger.
It gets bigger. We call that an increasing function. It has a vertical asymptote at 0. Okay, and so then there's nothing over on the left-hand side.
It's not a decay, it's a something, I forgot the word for it.
Well, it's not quite that kind of a thing because it's not an exponential. An exponential would be either a growth or a decay. This is growing, but it's very slowly growing. Okay? And so what we have here is that it is an increasing function, but the amount of increase or the rate of increase decreases. It's going up, but it slows down its progress of going up. And yet at the same time, it does not have a horizontal asymptote. It does go out here forever, and it does go to every y value, but it's very slow in doing that. So this is what a logarithm, just in general, looks like. And as it turns out, the growth rate is proportional to 1 over the x value. So when we say how fast is it going, if you say 1 over x, then this would be like 1/3, 1/9 out here. So it's a very slow thing here. But notice, as it goes close to 0, 1 over that number, like this one. If I say 0.1, 1 over 0.1 is 10. So that means it has a very steep slope over here, because the slope is like 1 over the x value. Now, of course, you'll get into that more when you get into calculus, but we won't do that right away. All right. So I just wanted to review that, kind of get us into the feelings that we have about this process. But then when we look at what we have here on the sheet, there is a mathematical number that's created specifically to use in exponents and logarithms. But before I do that, I just want to mention one other thing, because we're talking about some science today. I wanted to talk about some of the science in logarithms. As it turns out, your body and many biological things respond to stimulus according to the logarithm. So that when you hear something that's 10 times as loud as something else, your body only responds as though it were twice as loud. because your body responds to the logarithm of the stimulus. So that means that when you are out there and you say, wow, that's really loud, that thing that's really loud, it might be 10 to the 10th power as loud as something that's soft in terms of the energy of the thing. So there's a huge amount of range of ability for you to respond to stimulus because your systems respond in a logarithmic way. And that's true for sight, I know, and for hearing. So that if you're like in a very dim room, the actual amount of light might be 1 billion times less than it is in the sunshine. But your eyes are able to adjust to that amount of energy because your eyes are responding according to the logarithm. Anyway, that's just a fun fact. All right, so now we're going to talk about
Our
this
feelings.
thing. No, we should.
I'm just kidding.
I feel great, thanks. Okay, so then we go to the natural logarithm. What is this number? This number E. Well, here it is. E is the limit as n goes to infinity of 1 plus 1 over n to the nth power. This thing was discovered in the late 1600s. And what does it actually mean? Well,
1600s?
yeah, you know, like 400 or 500 years ago, people discovered this thing.
What? You were
Yeah.
smart. You're not lying, are you?
I'm not at all.
That's what I was like. They were really smart.
They were smarter than we are most of the time. But so let's talk about
How
something
dare you say
that's a 10% increase. And we talked about this a little bit last time. If I have $500
Oh, yeah.
and it increases by 10%, what happens in year number 1?
It's going to be 0.01? No, 10. No? Well, hold on.
How'd you get 550? Right?
Yes, 10% of 500 is $50.
Right? And then you add it, right? But as it turns out, there's an easier way to do that, and that is to take 500 multiplied by 1.10.
That's what I was trying to say.
Yeah, but that's not what actually happened. That is it. Okay, so then we take 500, we multiply it by 1.1, we get 550. What happens the next year?
It increases.
That's correct. How do we figure out the amount for the year 2?
Don't you add them?
I do
The
not.
exponent for the increase is going to be 2 now.
Okay, so now we're multiplying by that again, and so we get 1.10 second power. Okay. And then whatever that is, right? But this thing here, this thing that gets multiplied, that's telling us the increase that's actually happening based on this original $500. So then, what happens if I take this 10% increase and I do it over 10 years? That would be 1.10 to the 10th power, right? And that comes out to be approximately 2.59. Well, the banks, they have a certain thing that they do where they will not give you all the 10%,
Yeah.
but what they will do is they will say, let's make this happen more often. Instead of doing it just once a year, let's do it twice a year. Well, if you do it twice a year, they say, tell you what, we'll give you 5% twice a year. And that will actually make your money grow faster. Because you would take 500 and then you would do 1.05 to the second power. So tell me, what's 1.05 to the second power? We'll just not worry about 500 right now.
1.1025.
Okay. So if they do 5% twice a year, then it's actually a little bit better than a 10% rate. It's 10.25%. Well, then what if we did this? 1.05, and now we're going to do it 20 times, because we're doing it twice a year, we do it for 10 years. What do we get when we take 1.05 to 20?
It's gonna be 11.
No.
1.7103.
2.6. 53.
53, okay.
You want
Or
to
did
continue?
11.
No.
Oh, because
All right, so if we did 10% just once a year, that would give us this number. But instead of doing 10% once a year, we're doing 5% 2 times a year. So then that's going to grow a little bit more, not a lot more.
but it's not.
It's something, and so then the banks are like, oh yeah, this is good. And we're like, all right, great.
Yeah.
But what if they were to do this compounding 10 times every year and they gave you just 1%? Well, this would be 1.01. And for 1 year, it would be to the 10th power. But now we're going to do it for 10 years. So 1.01 to the 100th power. Well, that comes out to be 2.705. So what we're doing here is we're saying, all right, we're going to take something that grows, and we're going to think about it growing in a discrete time period, once a year or 10 times a year. We're going to say, increase it, boom, increase it, boom. But that's not how natural processes work. Okay? Natural processes, those bacteria that are out there, they're continually increasing, right? They're increasing all the time. So then, instead of saying it's 1.10 or 1.05 or anything like that, it's actually increasing all the time. But if you look at this particular number, this number is not going up a huge amount. It went up from 2.5965 and now 7. And then this is what they came up with in the 1600s. What happens if you take this thing and you call it continuous growth? That's where the number E comes from. E, which is approximately 2.78. So that number E is how actual things grow when you're talking about continuous growth. We're not talking about banks just deciding they're going to give you a certain amount. We're talking about chemical reactions and all this other stuff that's out there scientifically, right? So the name for this thing, if I put E instead of using all this other stuff, then it's called continuous compound. So we're adding to something and we're doing it continuously. So now we're going to use this idea, this number, which we come up with in a mathematically fancy way. We're going to now put this into an exponential function.
Mr. Bowers, before we
Yes.
continue, just to be clear, when we got 1.10, we're multiplying by 100, right? But it's 10% increase, but it's 1.10, it becomes 1.10 because we multiply by 1.
Okay, because we are saying you start with the amount of the material and then you increase it by 10%. So it's
So
like
that's
110%. Okay, right. Okay. So then, just to place this part over here.
He matched your shirt.
So then we say, all right, what happens when I actually graph this thing? So we're going to actually graph the thing. So we're looking at y is equal to 10 to the power of x. And then we're also going to do y is equal to 2 to the power of x. And we're going to look at the difference between those two things. So if I go to the using a 10 as a basis, that would be the red one. So hopefully it's clear. It goes up really fast, right? If I go over here to the number 1, it would go up to 10. And if I go over to 2, I'm up at 100. That's really fast, okay? This is 10 to the x power. That's the red one. Well, what's the blue one? It's 2 to the x power. So if I go over 1, it's 2. If I go over 2, it's 4. If I go over 3, it's 8. And so on. It's still going up, and it's going up pretty fast, but not as fast as this one. But then what happens if we go with this number e? That's the green one here. Well, I changed my ones. Forget what's on there. So I'll change this one. And this one. There we go. That looks like what you got. So I have 3 different things here. I have 10 to the x, which is going up very fast. 2 to the x, which is going up but not quite as fast. E to the x because it's in between. So then what actually happens here is that when I look at this e to the x power, the slope of this blue line is related to the y value. So if I look at the y value, which is 4, it's going up with a slope of 4. You can see if I go over 1, this goes up 4, basically. And if I go here to 2, this has a slope of 2. Because you can see here, it's about going over 1, and it goes up 2. So when I say my growth rate is based on how much I have. If I have more stuff, it goes up faster. Then that would make this 4. That makes this 2. Up here, this would be a 6, right? From here to here, that's 6, and it goes over 1. And it goes up 6. So this thing is increasing in its growth rate based on how much stuff I actually have. And that's how bacteria work, right? If I have a lot of bacteria, they increase very quickly. If I only have one little guy swimming around, then it increases very slowly. So when this happens, again, scientifically, this is an important relationship. So then, this is what's on your calculator. When you look on your calculator, you'll see an e, a lowercase e, and we're going to take that lowercase e to the 5th power and see what you get.
148.413.
Okay, 148.4. So e to the 5th power is way up.
So
How do you do that on a calculator?
Okay, so do you see a thing on your second that has an e to the x power?
Mm-hmm.
Okay, so you would write, you would hit that button and then the number 5, and then equals.
What did you say the answer was?
148.4.
did you get it? Need help?
I'll help her.
I have it. I just don't know which one it is.
Okay.
This one heard that.
The first thing you do. So,
This
yeah, second, that button, 5. There it is. All right, good.
Yay.
So this number, which is on your calculator, is what we use in science to describe these things that grow based on how much material you have tells you how much it's going to grow. That's where this number comes from. Now, any of these things have exponents in them, right? But, yes.
So that's E means it's a constant rows, kind of like it's a formula for finding things.
Okay, what E
Because
means.
the rows is depending on what you give it.
Right, depends on how much stuff you
Yeah.
have.
Yeah.
But the fact of the matter is, anything that has an exponent in it will also grow according to the amount of material.
Okay.
It's just that when you use the E in here, then there's an exact relationship. The slope of the line is the same as the Y vector. That's what's happening with the E. The rest of them are also growing according to how much stuff you have, but the E to the X makes those things correctly proportioned to each other. All right. So then, is this 10 to the X power, is this an exponential function? And the answer is yes, because it has an exponent and it's a function. This would also be an exponential function, right? But in mathematics, we call this the exponential function. So the rest of them are exponentials, but this is the exponential function. So if you're going to do, like on a spreadsheet, if you go to Microsoft Excel and you say, I want to find out what is E to the 5th power on Microsoft Excel. So I'm going to make that happen here. Make the font bigger. See it? I'm going to write EXP, parenthesis 5. I just did that. So the exponential function is E to the power of whatever it is. All right. So what happens then in science is that a lot of people want to use this number so they can compare different amounts of growth for different things. And so what they will use, and we'll just put this on pause for a minute. What they will use is this specific formula. Like this. A is equal to P times E to the RT power. Which is called PERT, right? P-E-R-T.
Like the shampoo.
Yeah. I didn't know that was still a thing. That thing came out in like 1980s.
Really?
Yeah, it's true.
All right.
How
So,
would you know?
I was a kid then.
oh, what?
Yeah.
All right. So we're looking at this right here, and we say
I know.
E to, you are. And then how this is actually explained is that this is my amount, right? Or you could say the compound amount. This is what I get. But then this P, this is my initial amount. This is how much you started with. You start with that, and then it grows, right? In fact, sometimes it's called A sub 0 because it's the value at time equals 0. So you start with an initial amount, and if you put in t is equal to 0, then it's just e to the 0 power, which is 1. So this would be your initial amount. This is what you're starting with. And then the r
Is that time equals to 0?
is, because this is a growing thing based on time.
Okay.
So t is time. And then r is, quote unquote, the rate. So what we can do then is we can think about this and we can say, if I have something that has a higher rate of growth, then I can put it in this formula and I can just change that number r. And that number r will make it grow either faster or slower. So then I can say, okay, well, that's what it is. That's how I get the rate of growth. Now, technically, it's not actually the rate of growth, all right? So let's say I have a rate of 10%. That would be 0.10, right?
Mhm.
And so then I would write this as e to the power of 0.10t. Okay?
Mm-hmm.
Well, what happens if t is equal to 10?
Cancel that.
So then e to the first power, right? Which is 2.718. But what happens if I take 1.10 to the 10th power? Well, we already did that, right? It's 2.59. It's not the same thing. Okay. So when somebody says, I'm going to use my exponential function, and I'm going to put in a rate of growth to be 10%, and they put a 0.10 in here, that doesn't actually mean it's growing by 10% every time. Because if it was growing 10%, we would use this, 0.10 or 1.10. This is 10% growth. This is not exactly 10% growth. But and I don't even know why people do this, but they say, oh, well, that's what it means. My rate is 10%. And that's not exactly what it means. But it is a way for us to use a formula and adjust it so that we can say R is equal to a particular number. So you'll see this out in the research that people do. They say, all right, well, what's your growth rate for this thing? And they'll say, oh, it's 15%. But what they actually mean is that R is 0.15. It's not exactly the same thing, but that's how they say it. So we'll let them have their fun. All right. So let's see if we can make this work for a particular situation. I have it written down here. I have a cake, and I'm going to take this cake out of the oven. Now, what happens when you take a cake out of the oven?
It's supposed to be warm. Well,
It is.
Oh, it is.
warmer than warm, I should say. So,
Yeah, it's hot, right? So I'm going to take out a cake.
do you have a cake?
I have a leftover piece at home, but I'm not able to eat it right now. Thanks for reminding me.
Well, no, thanks for reminding me.
Oh, that's true. I was the first one who said
Yeah.
cake. Now am I? I'm the first one who
Don't.
said cake. I can't put it off on you, even though I want to, but I'm not going to. So here comes the cake. It's out of the oven. And it is at 220 degrees. And it's going to cool off. And you think that it's going to cool off to be like the room temperature. And let's just say I'm in the kitchen, it's a little bit drafty and it's winter time. So it's 68 degrees. is this cake actually going to get to 68 degrees? Well, eventually it's going to get close enough that it won't matter, right? But the process is going to be one where it slowly decreases towards that 68 degree amount. And then here is our function. So it is the temperature as a function of time is equal to 68 plus 220 e to the negative 0.18 t.
Where did you get the 0.18?
This is from the rate of change of temperature for this particular cake. Okay? Everything that exists has its own chemical and physical properties, which are going to change this number. Like a metal will cool down quickly, whereas a clay pot, it'll take a long time. So these things right here depend on the situation with the physical object. So we're going to say that that's what it is right there. Okay. So now you have this, and it's on your sheet, so you can look at it. But let's put in some numbers. What happens when time is equal to 0? What's the temperature going to be?
Should theoretically be 68, right?
No, 68
Oh,
plus.
oh, I'm sorry, I made this wrong.
What?
This should be 288.
Hmm?
I made it wrong. Because
88.
if this is 0,
Mhm.
this makes the exponent 0. E to the power of 0 is 1. So this is 1 times 220. Right? So this is 68 plus 220.
Which is
So-
288.
It is. I'm sorry, I started off wrong. It's supposed to be 288.
What about there? It's not 88?
No, it's not, because
Okay.
it's 68 plus 220. And it's been so long since I've done this. This number here in front of the exponent is the amount of difference in temperature. So between the two of them, it's 220 degrees. So then how fast is that going to change? Now you know this, right? If you have like a frozen item and you take it out, it's going to take it a relatively long time to warm up. If you have something from the refrigerator, it doesn't take as long. And if you're taking something like from a cool room to a warm room, it's just going to change very quickly. So this is the concept here, right? That the amount of change or the rate of change depends on the amount of the difference. If it's a big difference, it changes quickly. If it's a small difference, it changes slowly. So just like with the bacteria and just like with the money in the bank, what the change rate is related to how much stuff you have. But notice that this is negative, which means it's going to be decreasing. All right, so let's do another number here. Let's put in 5. So I'm going to put a 5 in here for t. And actually, I can do this whole thing on my calculator just with one step, right? I can write 68 plus 220 multiplied by e to the power of, and I put this in parentheses, 0.18 times, negative 0.18 times 5. So this is what it looks like on your calculator. 68 plus 220 multiplied by e to the power of, in parentheses, negative 0.18 times 5. So that's what you want to do. And what happens when you put that into your calculator? 1.20 negative times 5 exponential. Where's it? Where's my E button?
157.44.
I'm looking at Microsoft's version of a scientific calculator,
157.44.
and it doesn't have exponentials on it.
Oh, damn
They're so lame.
it.
In the,
A decimal point,
whoa,
if that's what you're asking.
68 plus 220 times e to the power of negative 0.18 times 5, 157.44.
Yes.
So in 5 minutes, it's gone from about 300 degrees down to 150 or 160 degrees. That's a lot, right? 5 minutes, cool down significantly. What about in 10 minutes? So we're going to do the same thing, and if you have a graphing calculator, you can bring it back,
Yeah, just.
and then just change the 5 to a 10,
104.
104. All right, now the question is, do any of you ever use a thermometer when you cook?
Yeah, sometimes.
Sometimes.
Sometimes I use it too.
Actually, no.
Yeah, okay.
I know that's
It is my eyes.
but
All right, and so the fact that you're still alive means that you've been pretty lucky so far.
No.
Because you have to cook to a regular temperature in order to kill all the bad bacteria, right?
I don't even measure anything. I just
Yeah,
know with my eyes.
like I said,
It's
you're
true.
still alive, so I guess it's working out pretty well.
so do you put a lot of salt in your cookies?
No,
Oh.
actually, I've been told to open my own restaurant. I'm not exaggerating.
Oh, okay.
That's
Well,
how
yeah, that's fine. I'd go. I would.
Oh.
So then, how much did it change in the first 5 minutes? It was about 130 degrees. How much did it change in the next 5 minutes? Just 50 degrees.
Yeah.
So the amount of change
It's
is slowing down because there's not as much difference between the temperatures.
Oh.
How about 15?
Oh,
What happens to 15?
that's good.
Oh, I mean,
Let's see.
82.7.
82.8, so let's say 83.
50. Yeah, 82.
83 when we round it off correctly, sure.
Yeah.
And then 20 minutes,
we don't have to do
That
that.
is weird.
74 degrees. Now, if you're thinking, I want to eat this cake, right? You want to probably eat it warm. So you're probably not going to wait 20 minutes.
I'm so mad that he still doesn't have a cake.
I still don't. I'm still going to be talking about frosting,
So why
sprinkles,
are
and
you
all
talking
this stuff.
about cake right now? Just talk about beer.
Okay, so exactly. If you have a beer and you take the beer out of the fridge, and then you say, okay, what's going to happen to the beer?
Gonna get warmer.
It's going to get warm. Why doesn't it get colder?
Because of the room temperature.
The room temperature is higher, and so this is going up to the room temperature, right? But it warms up more degrees at the beginning, and as it gets close to that regular temperature, it's not going to warm up as much. That's how it works. If you have ice in a glass, right? At what point does the ice melt the fastest? It melts the fastest right away, as soon as you put it in there. After a while, it's like, well, this ice is never going to melt. It just sits there, right? Because the change is small, therefore the reaction happens more slowly. So this thing, the fact that the more of a difference you have, the faster the reaction happens. This is all over chemistry, right? Because it's the same thing. You have more stuff in the beaker that's reacting, it's going to react more quickly. If you don't have very much in there, it's already reacted. There's just a little bit left that hasn't, and so then it slows down reaction. It goes on. Very fun. Interesting enough, in chemistry, there are things that don't happen slowly, like explosions, right? Explosions don't happen slowly, they happen quickly. But it's all the chemistry and stuff, and I'm sure it's interesting.
Hopefully no one's in there.
Yeah, well, we're just talking about like a little beaker stuff, and you put the Mentos and the Diet Coke.
Yep.
All right. So this whole thing then, this is working with this exponential function. The exponential function that has this letter E in it, okay? And we talked about, and this is something that's not on our sheet here yet, but I'm going to make it happen here. And so we talked about exponential growth. We also have exponential decay, right? So on your sheet, you see these are growing, right? These are all growing. They're getting more as you go. But then what does decay look like?
It's decreasing.
It is. And so what we would have is e to the negative x. E to the negative x will flip the positive x and the negative x and flips it around the other way. So
Like the inverse function?
it's not the inverse function.
No, but
it's
something like that, we flip it over.
Okay, the inverse function, right? When we talk about that, the inverse function flips through this line.
Mm-hmm.
This negative here flips through this line. So it's going down that.
Okay.
Yes. All right. So if I have e to the negative x, then it's going to be
A mirror of it.
a mirror of it. Exactly right. So then we kind of zoom in a little bit here to see it. So then this purple one is e to the x. The blue one is e to the negative x. And again, it's the same kind of an idea, but here the amount of decrease is proportional to the amount of stuff. So here the slope is 4. You can see it goes over 1 and down 4. Here the slope is 3. It goes over 1, it goes down 3. Here the slope is 2, over 1, down 2. Here the slope is 1, or negative 1, I'm sorry. Negative 4, negative 3, negative 2, negative 1. Over here, about here, the slope would be negative 1/2. So the slope is negative based on how much stuff we have. Now, this again would be like a chemical reaction, right? How much stuff gets used up over time. But this is also what we call half-life. Because we say, what is half-life? It's probably a video game or something, but it's also
Also, when you're halfway dead.
you're halfway dead.
He's like, oh.
I think I already passed my expiration date as far as that goes. But half-life then is where we have, let's say we start with 1,000 bacteria. Okay, and they're in a certain kind of a chemical which makes them die, right? So then we're going to have a certain amount of time, and then we're going to have 500 of them. And then in the same amount of time, we're going to end up with just 250. And then 125, and so on. So that the half-life is a particular amount of time where we get half of the amount as what we had originally. So if we have something, just a graph of something, we can kind of estimate what that half-life thing is. I'm not going to require you to calculate half-lives, things like that. It's out there. It's something that you can do, but it's not something we're going to worry about. It turns out that if I had like 1,000 at the beginning, then it would be 1/2 to some k power. So that originally this would be 1,000, and then when you go to k amount of time, it's 500 because it's a half as much. And then you go k amount of time, it's now 250. So every time you go k, then it is half as much. You're multiplying by a half every time this k amount of time happens, whatever it is. And this is really big with radioactive things, because with radioactive things, this has been measured for various chemicals like carbon-14, for example. And so then you can say, this thing has some carbon-14 in it, and then you measure it and you say, well, it has this much. Well, how much did it start with, if you have some way of figuring this out, right? You say it started with this, and now it ends up with this, then I know how many years it took for that to happen. So people that are really smart have the ability to take some kind of Egyptian artifact, and they apply this process, and they can say, wow, this thing is 7,000 years old, or whatever. Now, like I say, I'm not a smart person when it comes to chemistry or stuff like that. I don't necessarily know that they know everything about what's going on, but it's a theory, and it works. All right, so that's enough.
So, Mr. Powers?
Yes.
Y equals to E to the power of -x, right?
Yes.
What if we had -3 and or x is already half x? Does it become +3 now?
Right. If
The exponent
if
becomes
we're
positive?
looking at a -3,
Yeah.
then that would become positive.
Okay.
And so then that would put us over here,
Okay.
which would be bigger.
Okay.
It's
And then-
bigger on this end.
Over there we have 1,000 times half k. Why isn't that negative?
Oh, because this right here
Uh-huh.
is 2 to the -1 power. So then I could rewrite this as
Okay.
1,000
Okay.
times 2 to the -. That would be, yeah, that's good. All right.
He's telling us to leave
I sure am.
the nicest way possible.
Okay, and just for fun, I'm gonna post a video for the.
So I have a question.
Okay.
Bye, people. Have a great day.
Yeah.